So now we'll look at the second part of problem number 16 from chapter 13, which says to get back to Earth you need to escape planet X. What minimum speed does your rocket need? And this is what we also call the escape velocity. So we'll use conservation of energy to solve this problem. We'll define 2 points. So the initial point is going to be starting at the surface of the planet. So this is where you're launching from. And the final point is going to be some infinite distance away. So some distance, let's say, as r goes to infinity, or you could say as the distance r is much, much bigger than the radius of planet X. So we're getting away from the influence of planet X. So using conservation of energy, what we'll say is that the initial energy is equal to the final energy, and we've defined our initial and final points in our diagram. So, what are the energies involved? You have initial kinetic, initial gravitational potential, you have final kinetic, and final gravitational potential. So what we're going to say is that to make solving the problem easier, that your final velocity at this final point is 0. So you have just enough kinetic energy at the beginning here, and yes, you have just enough kinetic energy to get out to your final point an infinite distance away where your velocity goes to 0. And so there is no final kinetic energy. Also, if you're an infinite distance away, if you're very, very far away from planet X, there's no potential energy. There's no gravitational potential energy associated with planet X. So now let's plug in on the left-hand side, because on the left-hand side we've got initial kinetic and initial potential, and we have both of those. So initially, we'll write our kinetic energy term 1/2 times the mass times the square of your escape velocity. And then filling in for gravitational potential energy, whereas remember there's a minus sign associated. Remember we talked about why that's true in class, that it's minus g times the mass of planet X over the radius of planet X. And those two terms equal 0. We zeroed out the terms on the right-hand side of that energy equation. So now, if we solve algebraically, and you also need the mass of the rocket in your gravitational potential energy term. So now, if we set both sides equal to each other, 1/2 m times the escape velocity squared equals g times the mass of planet X times the mass of your rocket over the radius of planet X. The mass of your rocket cancels on either side. The escape velocity with some algebra is the square root of 2 times g times the mass of planet X over the radius of planet X. But we can make some substitutions, right? Because we know how the mass of planet X and the radius of planet X relate to the mass of the Earth and the radius of the Earth. So let's go ahead and plug those in. So we have 2 times g times twice the mass of Earth divided by the square root of 8 times the radius of the Earth. And so now if we plug in, it's the square root of 2 times 6.67 times 10 to the minus 11 newtons times square meters over kilograms squared. Then you've got 2 times the mass of the Earth, 5.98 times 10 to the 24th kilograms divided by the square root of 8 times 6.37 times 10 to the 6th meters, the radius of the Earth. And if you plug all that in, you get 9,410 meters per second. So that is the escape velocity if you were to launch a rocket off of planet X. If you wanted to get a very large distance, basically escape the gravitational pull of planet X.